Welcome to our discussion on ratios and rates. Many books, this one included, tend to kind of overcomplicate this idea when they try and present it to you. So try not to get too confused. I'm going to simplify things for you, hopefully. Let's start with some definition. You should already be familiar with what a ratio is, but if not, it's just a comparison of two or more quantities. Most of them are just two, but you can do two or more. So if we say the ratio of one quantity is to another is 2 to 5, also written as 2 colon 5, right? So the colon is always written as, or spoken as the word 2. So it's 2, 2, 5. Then this means that for every 2 units of this first quantity, we have 5 units of the second quantity. And that gives us a nice little fraction. And now that we have a fraction, we can use our rules of multiplication. And we know that if I take this fraction and multiply top and bottom by 10, it's still the same fraction, right? 20 over 50 is still 2/5. So that means if I have 20 of the first quantity, I now have 50 of the second quantity. So ratios are basically just another version of fractions. I know a lot of you are quivering going, oh, I hate fractions. But they're not that bad, right? It's kind of a very simple version of fractions. So don't panic. Okay, rates are merely ratios also, which are also fractions. So rates are just a version of a ratio, but usually between two quantities with different units. So as before, when we were talking about 2 to 5, that was a ratio of two quantities, both measured the same thing. Like 2 pounds of this is equal to 5 pounds of that kind of thing. If you were making some sort of recipe and you had to put 2 pounds of flour to 5 pounds of, something else, that kind of idea. Here, we're going to have a certain amount of one quantity and then a certain amount of another quantity in a completely different measurement standard. Some of the common ones you've seen are miles per hour, where the first thing is measured in miles, i.e. your distance, and the second thing, time, is measured in hours. You travel 60 miles per 1 hour, 60 miles per hour. You could also say I did 120 miles in 2 hours. Hey, I drove 120 miles per 2 hours the other day. And you're like, wait, what? Don't you mean 60 miles per hour? Yeah, it's the same thing, right? So that also tells us that when we talk about rates, we normally let the second one be a 1 because it makes more sense. You could say, I type 43 words per minute rather than, 21 and a half words per 30 seconds. You're like, what? And then another one that you've seen is miles per gallon, and of course, deaths per 100,000 people or births per 100,000 people. Those are two examples where the second numbers aren't 1, the second numbers are 100,000. So, miles per gallon per 1 gallon, words per 1 minute, or deaths per 100,000 people instead of deaths per one. And the reason why we don't say deaths per one person is because it's smaller than 1, right? I mean, when you talk about deaths per 100,000 people, if you were just talking about, like, let's say by cancer, maybe the answer is 5,000 per or 5,023 per 100,000. Well, you can't do that per one person because then that would be a decimal and it wouldn't make sense. So that's why the second number is per 100,000 people. Now you could, do it per 100 people if it was something that happened enough. Like, left-handedness is maybe, let's say, 10% of the population. Then we would say 10 out of 100 people, that kind of thing. But if left-handedness was, less than 1%, then it would make more sense to have the number of people be 100,000 instead of just 100. But you get the idea that that second number just helps to kind of make the comparison of that rate easy to understand. All right, how about a table like this that might seem very confusing when you first look at it, but it really is just a bunch of ratios in disguise. So for instance, in 2005, there were 43,510 people killed. The population in thousands was this many, big, right? So the fatality rate per 100,000 is 14.72. And what the heck does that mean? Where did they get that number? Well, if you simply take deaths and divide it by total population, right? This is my A over my B. Then you get 0.1472. And you go, okay, well, then why is this 14.72? Well, remember, this was in thousands. This is in 100,000. So that's why you got to multiply it by 100. Because if you did this divided by this, that would give you how many deaths per 1,000, right? Because this is in thousands, this unit. But if we want deaths per 100,000, then we multiply by 100, and 0.1472 blah, 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 blah becomes 14.72. It really is just that simple. We're just doing ratios. So the rest of these things, as complicated and confusing as it looks, are just simple fractions. So again, if we take deaths and then divide it by the number of licensed drivers, this is in thousands, we would get a decimal. We would multiply it by 100 and then tell us how many were per 100,000 licensed drivers. This one's in thousands, this one's in 100,000. So if we did the ratio of that to that, i.e. that number divided by this number, again, a decimal, multiply by 100 to do that, and so on and so forth. You get the idea. It's very simple. One other example is this one where we're looking at these motor vehicle deaths. So this is numbers, right? This is just raw numbers. And then this is per 100,000 people. So now these numbers have been basically divided by the population and then normalized for however many in 100,000. So this means for every 100,000 people in the population, 10.39 people died from motor vehicle deaths versus 3 in Great Britain. And then over here, we can do it per 100,000 motor vehicles. So how many people died per how many vehicles that are on the road. And then this last one is how many people died per every 100 million vehicle miles driven. Well, in Great Britain, they use the metric system. So their original data would have been 3.7 motor vehicle deaths per 1 billion kilometers driven, and then you would have to convert that into 100 million miles driven, which would entail using a conversion line technique that we'll talk about in chapter 3. But I just want to point out that even when units of measure are different in the second thing, right? So deaths per miles versus death per kilometers, you can still compare those two quantities as long as you convert one to the other. We also could have converted ours into kilometers. Let's look at an example that has a lot of data, but don't panic. We look at this table here, which is showing you tuition and fees, room and board, and then total charges for different types of colleges: public, 2-year, 4-year, 4-year out of state, and then private, nonprofit, and for-profits. And then they have different years, right? So how much they paid in 2013-14 school year, and then the 2012-2013. This is how much it changed basically in raw dollars, right? It went from 31.54 to 32.64. It went up by $110, and that represents a 3.5% change. It went up by 3.5% from this year to this year. Now, if it was me, I would have put 2012-13 first and 2013-14 second, because it makes more sense to kind of read from left to right when we're talking about chronological. So that's one thing where this table is bad if you were going to make one of these. So I think as humans, we would rather see these two things switched. Now, with that in mind, we can compute some things. We can compute the ratio of private tuition and fees to public 4-year in-state tuition fees. So we're going to look at private tuition and fees, and we're going to look at total charges, right? Or in this case, just tuition and fees, right? So this is private tuition and fees for the year 23-14. So we're now in this first column. So we're looking at 30,000, and we're going to compare that to public 4-year in-state, which is this almost 8,900. And we're going to compare those two things when we scale the second quantity to 1 and when we scale the first quantity to 100. We can already see that if we're just looking at those two quantities, we can simply just do the ratio of those two quantities to get it. So looking at this number and this number, we can set them up as two different fractions, right? 8893 over 30,094, or, right, we can think of it as the other way around. So don't forget that these things can be fractions in either direction. All right, so here is just a piece of that table. We made our own little smaller table with the private tuition and the public. And we want the second one to be in a ratio of 1, so we need to figure out what this number is. And then for part B, they said, let's make this 100, and the second part, figure out what that is. Now, you don't always have to do this. You don't always have to make the second one 1 or the first one 100. That's just what they're asking for, and it's what this book tends to do. But we could easily trade places with these two things, and then, they trade places. The other one is 1 and the other one is 100. The bottom line is, usually when you're doing this, you tend to let the larger number be 100 and the smaller number be 1. Because we can understand, like 4 to 1, if this thing was 4 times as big, a lot easier than we can understand zero point 0.2 to 1. When we look at zero point 0.2 to 1, we don't immediately understand that zero point 0.2 is 1/5 as big as 1, right? That 1 is 5 times as big as zero point 0.2. But if we have 4 to 1, we immediately know that's 4 times as big, right? So that's why we normally let the bigger number be the x and the smaller number be the 1, because it just makes it easier for us to understand it. Same thing goes when we do the 100, because we think of this as percentage. So if this is 100 and this is smaller, this comes out to be 33, then we know it's 33%, or it's basically a third of it. But if we went the other route and this was 100 here and this was 300, you kind of have to think for a second, well, what does 300 mean to 100? If this is 100% and this is 300%, well, that's 3 times as big, right? But it's not as easy to understand. So that's why we tend to do it this way. But there's no rule that says it has to be that way. Okay, well, these are just like we did before, simple ratios. We're just looking at this number compared to this number, right? 30,000 over 8893 is going to equal x over 1. So if we do the math, right, you're basically kind of doing this cross multiplication thing, but don't do cross multiplication. X is already all by itself, and it's just divided by 1. So x just equals this. So just do the math. Do 30,094 divided by 8893 and solve. The only time you do cross multiplication is when you have a variable in the bottom and you need to bring it up into the top. So this is just silly waste of time, because look at, they do this, they set this equal to, and then to solve for x, they divide both sides by 8893, which it was already over here. Even if this was something other than 1, if this was a 4, then just multiply both things by 4 to get rid of this 4, and then you get this fraction, whatever it is, times 4 is going to equal x. So it's just stupid to do cross multiplication here. Just solve for x. And solve for x, just be smart. Just do the math. All right, so 3.4. So that tells you it's basically 3.4 times as expensive in tuition and fees for a private school as it is a public school, because that's what the 1 to 3.4 means. And if we did it the other direction, right, this would be 1, and this would have been a decimal, and it wouldn't have made as much sense. Now we can set up the other one the same way. With, before we did 30,000 over this equals x over 1. If we did that same ratio, we'd have 30,000 over this equals 100 over x, and x would be in the bottom of our fraction, and that's a lot more work to solve. So why not instead do 8893 over 30,000 equals x over 100 and solve it that way? Makes the math a lot easier. So let me show you what I'm talking about. See, with this table, these are ratios. Well, they could be a ratio this way. Here's my fraction line. This number over this number equals x over 1. But then 100 over x, yuck. But if we flip it this way, now all of a sudden, this number over this number is x over 100. And the math is a lot easier to do because we're simply just calculating, right? 8893 over 30,094 is x over 100. And if we want to solve for x, we're just going to multiply both sides by 100 to cancel that out. And then this is going to be our solution. Stick that in your calculator, and you can very easily, very quickly get the answer of 29.55. So that would tell you, if you went back to our table, that this tuition is roughly 29.55, or if you round it, 29.6% of this, right? Because that's really what's happening when you're comparing it to 100. For every $100 spent here, you only have to spend $29.6 here. Well, it's basically meaning it's 29.6% as expensive as that. Now, what if we wanted to bring in a third comparison? right? So we bring in a third column of information. We're now going to look at public 2-year tuition for in-state compared to the public 4 and the private. Well, now when it comes time to calculating the missing bits and pieces for the 2-year school, we can either use the ratio of the 2-year school to the 4-year school or the 2-year school to the private school. Now, the book is going to talk about using the public because it has a 1 and it makes the math easier than 3.4, and that is absolutely 100% true. But really, you should be using the public not because it has a 1, but because 3.4 is rounded. Right? We rounded that, and we don't want to use a rounded calculation to calculate something else and it can then round that one as well, because now we're compounding our rounding and our error is going to get bigger and bigger and bigger. So always when you're doing these tables, always go back to the ones that haven't been rounded. So if I want to calculate this ratio part here, I'm going to want to use the 1 and set it up simply as this ratio pair, right? This number over this number equals x over 1. So x equals this divided by this gives me 0.37. We round, we put 0.37 here. Now when it comes time to calculate the kind of the percentage piece, right, the piece out of 100, we don't want to use the public 4-year. We now want to go use this one. And we want to use this number and this to solve using the 100 because 29.6 was a rounded number. All right, let's finish off with one last example. So here's some similar data talking about prices of room and board, right, for a private school, and then room and board for a 4-year in-state, and then room and board for a 2-year in-state. The gray boxes are the things that we need to fill in, and I've already filled them in for us. This one's actually wrong, and I'm going to show you why. But let's go through how we got those numbers. Well, if we wanted to first, so let's say the first one we want to actually solve for is this. We want to figure out how did we get 1.18. Well, we look down the row and we have this number is given to us. So that means we want to be comparing these two numbers, right, and these two numbers. We want to create our ratio based on that. And we have to remember that the ratios are always sideways, right? If we think about these tables and rotating them this way or rotating them this way, that's what's really going on. We have this number over this number equals that number over that number. Okay, so I'll put it back. All right, so let's do the math. We have 9432 over 11118 equals 1 over x. Well, that's no good. I don't want x in the bottom because now I have to multiply both sides by x to get it out of the fraction. Then I have to divide both sides by this thing to solve for x. We have to kind of do cross multiplication, much stuff. No, you don't want to do that. This makes your life harder. So just flip it. Do 11118 over 9432 equals x over 1, right? Where this is x. We're solving for x. And now that's easy. Plug it into the calculator, we're done. And when we want to do this number, I'll do this one in blue. We'll call this one y. It's the same thing. We know that we want to solve for y, so we're going to put y over 1 is going to be, well, 8141, because that's the number that goes with y, right, over 9432. We can see this is smaller than 1, and that's where we get 0.86. Okay, in green, let's say we want to do this one. Well, now we look down the row, and we have this number, so we know we have to be using these two things. And again, this is my unknown. We'll call it z. So z over 100 has to equal, well, the z money over the 100 money. And now to solve for z, you multiply both sides by 100, and there's z. Okay, now this number, we'll do the last one in black. The reason why I got that one wrong is because when I went to calculate it, I did it based off of 8484. And remember, I told you you don't want to do that because that ends up rounding. So instead of setting up the ratio with these two columns, you want to go back to this one with 100. And, we'll say this is A. We're looking for A. So we're going to say A over 8141 is going to be, sorry, what am I doing? A over 8141, dummy. A over 100 is 8141 over 11118. And if you do that, right, then obviously multiply both sides by 100 to get rid of that. That's going to give you the correct answer to the correct decimal. It's going to give you 73.22. When you do it the other way, you get 73.23, which is slightly wrong, but wrong enough to, get marked wrong. All right, guys, that's everything you need to know for this chapter.